Properties of determinants. So far, we have learned to evaluate determinants by expanding them along any of their rows or columns. In this section, we shall study some properties of determinants which simplify its evaluation. By applying the properties, the determinants is transformed in such a way that a particular row or column has maximum number of zeros. These properties hold true for determinants of any order. We shall study these properties one by one. According to the first property, the value of the determinant remains unchanged if its rows and columns are interchanged. Let's verify. Consider the determinant delta as shown here. Expanding along first row, we get value of determinant as A1 multiplied by B2C3 minus B3C2 minus A2 multiplied by B1C3 minus C1B3 plus A3 multiplied by B1C2 minus C1B2. Now, by interchanging the rows and columns of determinant delta, we get the new determinant delta 1 as shown. Expanding delta 1 along the first column, we get the value of determinant equal to A1 multiplied by B2C3 minus C2B3 minus A2 multiplied by B1C3 minus B3C1 plus A3 multiplied by B1C2 minus B2C1. Using this property, we can conclude that if A is a square matrix, then determinant of A is equal to determinant of A transpose. Let us verify the property by example. Example. For the determinant delta shown here, verify that value remains same on interchanging the rows and columns. Expanding the determinant along first row, we have delta equals to 2 multiplied by 0 minus 4 multiplied by 0 plus 4 multiplied by 2 minus 5, which equals to minus 12. By interchanging rows and columns, we get delta 1 expanding along first row. Delta 1 equals to 2 multiplied by 0 minus 1 multiplied by minus 8 plus 1 multiplied by minus 20, which equals to 0 plus 8 minus 20 or minus 12. Let's now check the next property. If any two rows or columns of a determinant are interchanged, then the sign of determinant changes. To verify this property, let us take the determinant delta as shown here. Expanding along the first row, we get delta equals to A1 multiplied by B2C3 minus B3C2 minus A2 multiplied by B1C3 minus B3C1 plus A3 multiplied by B1C2 minus B2C1. Now, interchanging the first and third rows, the new determinant obtained is given as delta 1 as shown here. Expanding along third row, we get delta 1 equals to A1 multiplied by C2 B3 minus B2 C3 minus A2 multiplied by C1 B3 minus B1 C3 plus A3 multiplied by B2 C1 minus B1 C2. On further simplifications, we have delta 1 equals minus of A1 multiplied by B2 C3 minus B3 C2 minus A2 multiplied by B1 C3 minus B3 C1 plus A3 multiplied by B1 C2 minus B2 C1. Clearly, delta 1 equals minus delta. Similarly, we can verify the result by interchanging any two columns. We can denote the interchange of rows, ith row and jth row by placing the double arrows between them, and similarly for the columns. For the determinant given here, verify that on interchanging rows or columns, its value gets multiplied by -1. Expanding the determinant along first row, we have delta equals to 2 multiplied by 0 minus 4 multiplied by 0 plus 4 multiplied by 2 minus 5, which equals to minus 12. Now interchanging rows R2 and R3, we have new determinant delta 1. Expanding the determinant delta 1 along first row, we get 2 multiplied by 0 minus 4 multiplied by 0 plus 4 multiplied by 3, that is 12. We can see that delta 1 equals to minus delta. Hence, property 2 is verified. Next property is, if any two rows or columns of a determinant are identical, that is, all the corresponding elements are same, then the value of determinant is 0. Let's prove this property. From the previous property, we have seen that the value of determinant become its negative when any of its rows or columns are interchanged. But if we interchange the identical rows or columns of the determinant delta, then delta does not change. Therefore, delta is equal to minus delta, or twice of delta equals to 0. Therefore, delta equals to 0. Find the value of determinant given here. In the given determinant, R1 and R3 are same. Let's expand the determinant along first row. We get delta equals to 4. 4 multiplied by 8 minus 8 minus 2 multiplied by 8 minus 16 plus 4 multiplied by 4 minus 8. This is further equal to 4 multiplied by 0 minus 2 multiplied by minus 8 plus 4 multiplied by minus 4. That is 16 minus 16, or 0. Hence, the value of determinant is 0. Next property is, if each element of a row or column of a determinant is multiplied by a constant, say k, then its value gets multiplied by the same constant k. Let's verify the property by taking the determinant delta as shown here. Multiply the elements of the first row of the determinant delta by k. Let's call this new determinant as delta 1. Expanding along the first row, we get the value of delta 1 equal to Ka1 multiplied by B2C3 minus B3C2 minus KB1 multiplied by A2C3 minus C2A3 plus KC1 multiplied by A2B3 minus B2A3. Taking K common, we get value of determinant as K delta. Hence, the result is verified. By this property, we can take out any common factor from any one row or any one column of the given determinant. For example, consider the determinant delta. Here, we can take 4 common from the row 1. Using the property that the value of determinant is 0 if any two of its rows are identical, we get the value of delta to be 0. So, we can conclude that if the corresponding elements of any two rows of the determinant are proportional, then its value is 0. Moving on to the property 5, if the elements of a row or column of a determinant are expressed as sum of two or more terms, then the determinant can be expressed as sum of two or more determinants. For example, the determinant with first row as A1 plus lambda 1, A2 plus lambda 2, A3 plus lambda 3, row 2, B1, B2, B3, and row 3, C1, C2, C3 can be expressed as the sum of two determinants. First, with row 1, A1, A2, A3, row 2, B1, B2, B3, row 3, C1, C2, C3, and second with row 1, lambda 1, lambda 2, lambda 3, row 2, B1, B2, B3, row 3, C1, C2, C3. Let's verify the property. Consider the left-hand side. Expanding the determinants along the first row, we get the value of determinant as A1 plus lambda 1 whole multiplied by B2 C3 minus C2 B3 minus A2 plus lambda 2 whole multiplied by B1 C3 minus B3 C1 plus A3 plus lambda 3 whole multiplied by B1 C2 minus B2 C1. On simplification, we get the value of determinant is actually sum of the values of two determinants, first with row 1, A1, A2, A3, row 2, B1, B2, B3, row 3, C1, C2, C3, and second is determinant with row 1, lambda 1, lambda 2, lambda 3, row 2, B1, B2, B3, row 3, C1, C2, C3. On solving the determinant, we get LHS equal to RHS. Example. Show that value of determinant shown here is 0. We have determinant row 1 x, y, z, row 2 x plus 2a, y plus 2b, Z plus 2C, and row 3, ABC. This can be written as sum of determinants first with row 1, XYZ, row 2, XYZ, row 3, ABC, plus second determinant with row 1, XYZ, row 2, 2A, 2B, 2C, and row 3, ABC. Now take 2 common from the second row of determinant 2. By using the property, if each element of a row of a determinant is multiplied by a constant k, then its value gets multiplied by k, we get the determinants as shown. In the first determinant, the first row and second row are same, while in second determinant, row 2 and 3 are identical. Again, using the property, if any 2 rows or columns of a determinant are identical, that is, all corresponding elements are same, then value of the determinant is 0. We get the value of both the determinants to be 0. Hence, the solution is 0 plus 0 is equal to 0. Property 6. If, to each element of any row or column of a determinant, the equi-multiples of corresponding elements of other row or column are added, then the value of determinant remains the same. It means that the value of determinant remains same if we apply the operation Ri goes to Ri plus Krj, or Ci goes to Ci plus Kcj. Let's verify the property. Consider the determinant delta as shown here. Applying row 1 goes to row 1 plus k times row 3. Determinant modifies as shown. A1 plus kc1, A2 plus kc2, A3 plus kc3. Row 2, B1, B2, B3. Row 3, C1, C2, C3. Here we have multiplied the elements of the third row R3 by a constant k and added them to the corresponding elements of the first row R1. Now, using the previous property, the given determinant can be expressed as the sum of 2 determinants. First determinant with row 1, A1, A2, A3, row 2, B1, B2, B3, row 3, C1, C2, C3, plus determinant 2 with row 1, KC1, KC2, KC3, and row 2, B1, B2, B3, row 3, C1, C2, C3. Taking k common from row 2 of second determinant and the property that the value of a determinant is 0 when 2 of its rows are identical, we have delta 1 equals delta plus 0. Hence, the property is verified. Example. Without expanding, prove that the value of determinant is 0. Applying row 1 goes to row 1 plus row 2 to delta, we get determinant with row 1, x plus y plus z, y plus z plus x, z plus x plus y, and row 2 and 3 same. Taking x plus y plus z common from the first row, we have x plus y plus z multiplied by determinant whose first and third row are same. Therefore, the value of determinant equal to 0.